Hello everyone, my name is François Robinet and I'm a PhD student at the University of Luxembourg. Today, I will be presenting recent work from colleagues and I on the topic of weakly supervised free space segmentation. In this work, we are considering single images taken from a road-facing camera placed in a moving vehicle. We are attempting to classify every pixel as either free or occupied space. For evaluation, we have used the popular Cityscapes dataset, which provides around 3,500 finely annotated frames. Evaluation of a segmentation model usually distinguishes different types of predictions, as illustrated on this example. Green represents correct free space predictions, red outlines incorrect ones, and orange is used for free space regions that are missing from our prediction. The blue area denotes pixels that are ignored, either because no ground truth exists for them in Cityscapes, or because they are ambiguous. The main evaluation metric used in segmentation problems is intersection over union, which captures the overall quality of a prediction. Note that we also report precision and recall measurements in our paper, but they are omitted here for the sake of brevity. Since Cityscapes provides ground truth annotations for all its training frames, the first possibility is to use a fully supervised approach. We therefore start by training a segmentation model using pixel-perfect ground truth. In this case, we are using a typical UNet architecture based on a ResNet 18 backbone, and this is able to reach an impressive 94% IOU. As we have just seen, fully supervised segmentation works well, but it also suffers from a few important drawbacks. First, pixel-wise annotations are expensive to obtain. Second, it is impossible to annotate a set of images representing all the variations in the environment we expect at runtime. For example, roads look completely different depending on the country, the type of pavement, the time of day, or the weather. Ideally, we would like to be able to exploit unlabeled datasets, which are much easier to collect. For this reason, we use a weakly supervised approach, which does not require any ground truth annotation. Following Tsutsui et al., we generate weak free space labels by extracting superpixel features from a dilated ResNet that was pre-trained on ImageNet. We then cluster these features using k-means in order to obtain approximate weak labels. The predictions obtained using this technique are a good baseline, since they reach a test IOU of 79%. However, we observed that weak labels sometimes fail catastrophically, which prompted the question of whether we can reach better performance by training a model using these noisy labels. Surprisingly, training our UNet on the weak labels rather than the ground truth already improves over the raw weak labels by 2.5%. However, we can do better if our training procedure takes label noise into account. Our approach builds upon a technique called co-teaching, which was originally introduced for classification problems. The method relies on the intuition that models start by learning easier patterns in the data they see. Noisy labels are therefore usually harder to fit and will incur larger losses during early epochs. To filter out some of the noise, co-teaching therefore rejects some of the samples that have the highest losses. Stochastic Co-Teaching trains two models in parallel. Given the same batch of data, each student computes their own pixel-wise loss in steps A and B. In step C, each student samples a given subset of pixels with probability inversely proportional to their loss. Finally, in steps D and E, each student trains using only pixels that the other has selected to be relevant, similar to how two humans could teach each other. In this result table, we compare our approach to the three approaches that have already been presented. Compared to standard training, co-teaching is able to improve IOU by 0.7%. Since co-teaching trains two students in parallel, we also ensemble them and observe more improvement, especially in the stochastic case. I will conclude this presentation with a quick summary of our contributions. Our work adapts co-teaching for segmentation tasks and proposes a stochastic co-teaching variant. We show that this variant more effectively filters out label noise in this specific task. Our best model reaches 87% of the IOU, 93% of the precision, and 93% of the recall of the equivalence fully supervised baseline while using no human annotation. I thank you very much for your attention and hope you enjoyed this short talk. I'll be happy to answer any questions you may have.